Carbonated soft drinks, the most dominant beverage empire on the planet, are consumed at a staggering 340 billion liters per year, enough to submerge the Great Pyramid of Giza beneath a 150-meter-deep sea of soda. Behind those sparkling bubbles and the instant burst of refreshment lies an industrial machine operating with absolute precision, consuming millions of tons of agricultural raw materials and billions of cubic meters of water every single day. But have you ever wondered, how are tens of thousands of soda bottles produced in just 1 hour? In this video, step inside some of the most advanced carbonated beverage production lines in the world, where agriculture and technology converge to create one of the most controversial yet powerful products in the history of modern consumer culture. Did you know there's a soda that captured American taste buds 1 year before Coca-Cola was even created? That soda is Dr. Pepper, the result of a successful blend of 23 secret ingredients, originally formulated to mask the bitterness of medicine, transforming it into a fashionable soft drink that has endured for more than a century. The journey of every can begins in 10,000-gallon steel tanks at the historic Waco, Texas facility, the production site closely associated with the brand's iconic museum. To build the foundation for its 23 complex flavor layers, water first passes through a multi-stage filtration and reverse osmosis system, achieving near absolute purity before being combined with corn syrup and phosphoric acid. But the true key lies in the next step. The secret flavor concentrate is added in 2 separate stages to preserve the consistency of the signature formula. After being blended at a 5-to-1 ratio, the syrup mixture is rapidly chilled to 1.7 degrees Celsius, the ideal temperature that prepares the liquid to efficiently trap carbon dioxide molecules during the carbonation stage that follows. Taking advantage of this deep chilled state, the syrup stream is pumped into a saturation unit known as the carbocooler. Here, food-grade CO2 is injected directly into the liquid under high pressure. Because the mixture has already been cooled to a low temperature, the gas dissolves completely and remains stable within the liquid, creating the intense effervescence and signature burst of fizz released the moment the can is opened. To maintain this saturated state, the finished beverage is sent directly into high-speed filling lines. Glass bottle lines can reach speeds of 500 units per minute, while aluminum can lines surge to as many as 1,500 cans per minute. The moment each container is filled, a sealing machine crimps the lid in an instant, locking in the internal carbonation pressure. Finally, robotic arms and automated conveyor systems stack the packaged drinks onto pallets with precise coordination, ready to deliver this legacy flavor to markets around the world. In 2024, Dr. Pepper made headlines by officially surpassing Pepsi to become the second best-selling soft drink brand in the United States, behind only Coca-Cola. However, domestic success does not automatically translate into global dominance. In many international markets, Dr. Pepper does not operate its own independent bottling network and instead relies on competitors such as Coca-Cola or Pepsi for production and distribution. This dependence, combined with its complex flavor profile balanced between cherry notes and herbal undertones, has made Dr. Pepper a peculiar force in the soda industry. Deeply rooted in Texas, dominant among the loyal American consumer base, yet still a selective and niche presence on the global consumption map. Arriving 8 years after Dr. Pepper, Pepsi, originally formulated as a digestive aid, accelerated rapidly into a global empire, generating more than $90 billion in annual revenue. But have you ever taken a sip of Pepsi and wondered, what truly sets it apart from Coca-Cola? And why has this giant remained strong despite entering the cola flavor war as a late challenger? The journey of every can of Pepsi begins with groundwater drawn from the Oligocene geological layer, an ancient source known for its exceptional natural purity. However, to meet the demands of high-speed production lines, the water must still undergo a rigorous technical purification process. First, quartz sand filtration tanks remove all suspended impurities. Immediately afterward, reverse osmosis (RO) technology operating under extremely high pressure forces the water through ultrafine membranes, measuring just 0.0001 microns, smaller than a bacterial cell. This stage completely eliminates minerals and microorganisms, transforming the water into a chemically neutral solvent. Returning the water to this state of absolute neutrality is a mandatory standard. It creates the ideal foundation for blending with syrup concentrate, ensuring that every can of Pepsi, anywhere in the world, maintains a nearly identical flavor structure. Once the water base has been fully standardized, it is directed to the storage area housing the most critical ingredient, concentrated syrup. From sealed holding tanks, the syrup concentrate is pumped into the blending section and transferred into large-capacity stainless steel vessels. Here, automated dosing systems combine the concentrate with purified water and sweeteners according to pre-programmed ratios. Mechanical agitators and flow sensors ensure the mixture reaches complete uniformity before moving on to the next stage. To create its signature sweetness, the facility uses liquid sweeteners. In the United States, typically high fructose corn syrup, while many international markets rely on cane sugar syrup. In a standard 330 milliliter can of Pepsi, the sugar content generally ranges between 35 and 39 grams, equivalent to roughly 9 to 10 teaspoons. In terms of acidity structure, Pepsi primarily uses phosphoric acid, similar to many other cola beverages. However, the calibrated balance between sugar, acid, and flavoring components produces a rounder sweetness, smoother finish, and less dry aftertaste compared to competitors within the same segment. However, sweetness is only half of the story. The other half lies in the burst of refreshment released the moment the can is opened, a sensation determined by the cooling and CO2 saturation process. After physicochemical standardization, the mixture is sent into a carbo-cooler system, where it is rapidly chilled to 1 to 2 degrees Celsius. At this stage, food-grade CO2 is injected under high pressure, forcing the gas to bind tightly within the liquid structure before moving on to the filling stage. Pepsi typically maintains a carbonation level of 3.5 to 4.0 volumes. This means that each liter of liquid contains nearly 4 times its own volume of dissolved gas under standard conditions. This parameter is precisely calibrated to generate fine, sharp bubbles that deliver the signature tingling sensation on the tongue and maintain a lively effervescence even when poured over ice. Immediately afterward, the entire product stream moves directly into the rotary filling carousel within a sealed environment. Isobaric filling technology allows PET plastic bottles to be filled without excessive foaming, preserving the precise level of carbonation that was just infused. Instantly, high-speed capping machines seal each bottle with calibrated pressure. At speeds reaching up to 1,500 bottles per minute, that means 25 finished bottles of Pepsi leave the filler every second. But before officially exiting the production line, technicians randomly collect samples for laboratory analysis, rechecking Brix levels and actual carbonation pressure. At the same time, defect detection systems equipped with X-ray scanners and optical sensors inspect every bottle. Any unit with a liquid level deviation of just 1 to 2 millimeters or a slightly misaligned cap is automatically ejected from the line without hesitation. Finally, approved bottles are grouped into multi-packs and pass through a 180 degrees Celsius heat tunnel. Here, shrink film tightly conforms to the surface, forming a stable transport unit that protects the product from physical impact. This process ensures an optimal shelf life of 6 to 9 months for PET plastic bottles and up to 1 year for aluminum cans, thanks to the metal's superior resistance to light and oxygen penetration. From this point, tens of billions of Pepsi products leave factories each year and flow into a vast global distribution network. Although present in more than 200 countries, the United States remains the company's core market, contributing more than half of the corporation's total revenue. Yet even with a massive operational engine, Pepsi still faces the most fortified stronghold in the beverage industry, Coca-Cola. So what enables this more than 130-year-old giant to maintain its global leadership, delivering approximately 1.9 billion servings consumed every single day? Unlike PepsiCo's more centralized production model, Coca-Cola operates through a global, franchised bottling structure. The parent company focuses primarily on producing its concentrated syrup at key strategic facilities, then distributes it to more than 225 independent bottling partners worldwide. These partners complete the final product according to localized water and carbonation standards, allowing Coca-Cola to scale globally without directly operating every manufacturing plant. Most importantly, the core difference lies within the blending tank, where the art of balancing sweetness, acidity, and flavor structure creates an identity fundamentally distinct from Pepsi. Each batch of highly concentrated syrup, a formula that remains 100% confidential, is poured directly into stainless steel tanks, along with purified water and liquid sweetener. From a technical standpoint, Coca-Cola maintains a slightly higher level of phosphoric acid than Pepsi, producing a sharper initial impact on the front of the palate. This acid structure functions as a balancing mechanism, quickly cutting through sweetness and delivering a drier finish after swallowing. Finally, the packaging lines can reach speeds of 40,000 to 60,000 bottles per hour, while maintaining extremely low pressure deviation tolerances. In practice, around 60% of Coca-Cola's global output is packaged in PET plastic bottles, a familiar format on supermarket shelves due to its lightweight, low cost, and efficiency in long-distance transportation. However, PET does allow minimal gas permeability over time, leading to gradual reductions in CO2 pressure and subtle changes in flavor structure throughout the product's shelf life. For this reason, aluminum cans and glass bottles, which are virtually impermeable to gas, are still regarded as the gold standard for preserving the beverage's original flavor integrity. Completely different from the warm, robust flavor structures of the three cola brands above, Sprite, the youngest of the group, launched in 1961, made a remarkable surge to become the world's #1 lemon-lime soda, generating more than $5 billion annually for the Coca-Cola Company. Notably, although it originated in the United States, China is now the largest Sprite market in the world, contributing more than 1/4 of the brand's total global revenue. In the world's most populous nation, Sprite is more than just a soft drink. It has become a staple ingredient in fruit tea blends and street beverages, helping to build an extensive consumption network centered around lemon-lime soda. The journey of making a burger begins inside massive industrial mixers, where flour, yeast, water, sugar, salt, butter, and eggs are adjusted according to McDonald's proprietary formula, a system of ratios that exists only within internal production specification sheets. Inside the factory, the dough is never kneaded by hand. It is pressed, stretched, and twisted by machines capable of handling 1-2 tons per batch, spinning at over 100 revolutions per minute. After mixing, the dough is transferred to a controlled proofing stage, where the temperature is maintained at around 30 degrees Celsius and humidity is kept stable to allow the yeast to perform at its optimum. Next, the dough is automatically divided into precise portions, typically ranging from 60 to 70 grams, a figure carefully calculated so that, once baked, Each bun reaches a diameter of about 10 centimeters, fitting perfectly with a standard hamburger patty. Before entering the oven, the surface of the buns is misted with steam and coated with a thin layer of egg wash, creating the signature golden color. In less than 12 minutes of baking at temperatures above 200 degrees Celsius, thousands of identical buns are completed, uniform, precise, and ready for the next stage of the production line. Once cooled, the buns are cleanly split in half by an automated slicing machine, ready for the packaging stage. The bun halves are then placed onto conveyor belts, neatly aligned and sealed using airtight packaging systems, helping preserve freshness and optimal flavor. In a hamburger, cheese is not just added for richness, it is engineered to melt at precisely the right moment. Most major burger chains use processed cheese, often based on cheddar or American cheese, enhanced with emulsifying salts to control its structure when exposed to heat. As a result, the cheese begins to soften at around 60 degrees Celsius and fully melts at approximately 75 to 80 degrees Celsius, evenly coating the patty without separating into oil or clumping. A change of just a few percentage points in moisture or fat content can cause the cheese to melt too quickly or unevenly, disrupting the familiar smooth, creamy sensation of a perfectly made hamburger. Once the buns are completed, the production line immediately shifts to preparing the meat patties. On a parallel processing line, the patties are handled within a closed system, beginning with the selection and cutting of beef into standardized sizes, before being fed into high-capacity grinders to create a smooth, uniform mixture. What few people realize is that each patty does not come from a single cow. Rather, it is the result of a carefully controlled blend from around 200 cattle per day, designed to lock in flavor and ensure that every burger leaving the factory delivers the same familiar taste. Once the meat mixture reaches a smooth, cohesive texture, it is fed into patty-forming machines, systems programmed with near-absolute precision. Here, the meat is pressed into perfectly round patties, with thickness and structure tightly controlled. Pre-calculated pneumatic pressure ensures each patty is firm to the touch without cracking or breaking. Immediately after shaping, the patties are sent through a rapid chilling stage where powerful streams of cold air reduce the temperature to around 0 degrees Celsius in just 3 to 7 minutes. This process locks in the meat's structure, preserving moisture and ensuring an ideal tender texture when the patty is later cooked. When all the ingredients are ready, a McDonald's burger begins to be assembled through a process that has been standardized to near perfection. The bun is placed onto a hot grill for just a few seconds, enough for the surface to lightly toast and release its signature buttery aroma, while the inside remains soft and familiar. A layer of McDonald's signature sauce is applied with precision using a calibrated dispenser, just enough to bind the components without soaking the bread. Next, the layers are stacked in a pre-programmed order. Finely shredded lettuce for a fresh crunch, evenly sliced pickles for that familiar tang, a perfectly cooked beef patty, and on top, a slice of cheddar cheese that melts at exactly the right moment. Not too early, not too late. The entire process takes only 30 to 40 seconds, yet the result is a burger with a consistent flavor profile, whether you take a bite in New York, Tokyo, or Paris. That is how McDonald's turns a simple burger into a global product. We leave behind the McDonald's factory, where hamburgers are replicated every second. Next, we turn to another empire, the world's most globally widespread fried chicken chain, operating a machine worth tens of billions of dollars each year, KFC. The journey of KFC chicken begins at dawn, when refrigerated trucks carrying fresh poultry leave the farms and head straight to the processing plant. where every step is timed down to the second. Upon arrival, the chickens are pre-cleaned and immediately fed into an automated production line with almost no downtime. Within minutes, they reach the leg separation area, where industrial cutting blades, calibrated to match the natural structure of the joints, operate continuously at a capacity of around 10,000 units per hour, ensuring uniform sizing. The carcasses are then transferred to the evisceration stage, where vacuum-based systems remove the internal organs in just 3 seconds. The pressure is precisely controlled, strong enough to clean thoroughly, yet gentle enough to preserve the integrity of the meat, marking a critical step in maintaining hygiene, quality, and consistency before the chicken moves on to the next stages of processing. Immediately after the initial cleaning and sorting stage, the chickens are transferred to a dedicated wing cutting line. Here, each bird is placed into a mechanical positioning mold that holds it in the correct orientation before automated blades make precise cuts at the wing joints. This entire section is designed to operate continuously in production shifts lasting up to 18 hours per day, ensuring a stable supply for thousands of restaurants across the same region. Once separated, the wings are moved onto a separate conveyor for inspection and classification. The remaining carcass then enters the central processing line. Throughout this sequence, from halving the body to separating the breast and sorting the thighs, the ambient temperature is maintained below 10 degrees Celsius to slow microbial activity and preserve the meat's structure. The body is split along a fixed axis. The breast is removed using controlled pulling force, and the thighs are routed to a separate line, all to ensure that each piece of chicken behaves almost identically when it later enters KFC's pressure fryers. From this point on, the chicken enters the most critical stage, where KFC's legendary recipe is finally activated. On an automated conveyor, the chicken moves continuously through the dry coating station, a secret blend of 11 herbs and spices, including salt, black pepper, paprika, garlic powder, onion powder, mustard powder, celery powder, dried ginger, oregano, thyme, and white pepper. The key does not lie in the ingredient list alone, but in the blending ratios and the order in which the chicken comes into contact with them. As the first dry coating is applied, the spices adhere directly to the surface of the meat. The wet coating that follows dissolves part of the essential oils, awakening the aroma. Finally, a finishing layer of dry coating locks the entire structure in place, laying the foundation for the crispy, aromatic, and richly flavored crust that defines KFC's pressure-fried chicken. Once the chicken pieces have been pre-processed and coated at the factory, they are transported under refrigeration to individual KFC restaurants and enter the final cooking stage. In the kitchen, the chicken is kept at low temperatures until frying time, then placed directly into pressure fryers, the key equipment that defines KFC's cooking method. The frying oil is heated and maintained at around 170 to 175 degrees Celsius. Thanks to this high-pressure environment, the chicken cooks faster without drying out. The outer coating becomes distinctly crispy, while the meat inside remains tender and juicy. Frying times are strictly controlled for each product type, after which the chicken is removed, drained of excess oil, and transferred to warming trays. The entire in-store process is designed so that every batch of chicken served has the same color, texture, and flavor, regardless of who prepares it or what time of day it is cooked. Alongside its traditional bone-in fried chicken, KFC has developed small chicken pieces by cutting boneless chicken into bite-sized portions, rather than grinding or molding the meat like industrial nuggets. Each piece remains whole muscle chicken, simply divided into smaller cuts to suit faster eating habits and shareable meals. Thanks to their smaller size, these pieces cook faster and more evenly in pressure fryers. With temperature and pressure tightly controlled, frying time is reduced by around 20 to 30% compared to larger cuts, while the meat inside stays tender, juicy, and well hydrated. At the same time, the coating fully covers the surface, creating a deeply crispy, evenly golden crust that delivers KFC's signature flavor. Pringles was born as a revolution, a bold attempt to end the long-standing frustrations of traditional potato chips, too oily, too fragile, and bags full of air. Behind this daring idea was Frederick Bauer, a food scientist and chemist at Procter & Gamble, who transformed potatoes and snacking itself into a symbol of engineering precision. With over $3 billion in annual revenue, Pringles has become one of the most powerful snack brands in the world. The United States alone accounts for more than $1 billion in sales, making it the brand's largest market. Today, the iconic cans, featuring the mustached gentleman, are found in over 150 countries, each tailored with flavors refined to match local tastes and cultures. The most remarkable feature lies in its hyperbolic, paraboloid shape, mathematically designed for the perfect curve, allowing each chip to fit snugly in its can, evenly distribute pressure, and maintain flawless crispness. Containing only 42% potato, the rest made for rice and wheat flour, every chip is molded with millimeter precision. In a world ruled by spontaneity, by Lay's and Doritos, Pringles chose the path of calculated precision. So if you could only choose one chip, would you pick spontaneity or perfection? And now, let's travel to Idaho, where the cool climate and elevation of over 1,200 meters and the loose, fertile alluvial soil from the Rocky Mountains have created some of the most ideal conditions on Earth for growing potatoes. As Idaho enters early autumn, massive potato diggers begin to roll across the endless potato fields stretching to the horizon. At the front of each machine lies a dual-blade digging system with automatic depth control, guided by underground sensors. As the machine moves forward, the steel blades cut about 20 centimeters deep into the soil, gently lifting entire rows of potatoes to the surface. Immediately after, the vibrating screen mechanism kicks in, generating thousands of subtle tremors that separate soil, roots, and pebbles without scratching the delicate skins. Each row of freshly unearthed potatoes is then laid neatly on the field, ready for the next stage of collection. Behind them, specialized potato harvesters follow in formation. At the front, hydraulic lifting arms gently gather each row of potatoes, feeding them onto a vibrating conveyor that shakes off any remaining soil. Next, a 180-degree rotating belt transfers the clean potatoes into parallel transport trucks, each capable of carrying up to 25 tons. On average, a single harvester can process 500 to 600 tons of potatoes per day, equal to the work of more than 300 manual laborers. Inside the cabin, the operator oversees the entire process through a central touchscreen display, where data such as speed, vibration, soil moisture, and temperature are updated in real time. Each potato here is the result of months of meticulous care. Planted in April, watered by pure snowmelt from the Rocky Mountains, and bathed in long hours of sunlight unique to this high-altitude plateau. By the time autumn arrives, the tubers have accumulated nearly 20% dry starch content, giving them a firm texture, sweet and nutty flavor, and the remarkable ability to stay fresh for months after leaving the field. The freshly harvested potatoes then move onto the pre-sorting line. On the conveyor belt, each tuber is carefully inspected, and any that are too small, misshapen, or damaged are removed. From here, the selected potatoes are transported into massive cold storage facilities. Inside, the temperature is maintained between 7 to 10 degrees Celsius, with a relative humidity of around 90 to 95%, the ideal range for long-term storage. If the humidity drops too low, the potatoes begin to lose moisture, their skins wrinkle, and the flesh becomes soft, reducing starch quality and natural sweetness. Under these controlled conditions, the potatoes stay firm, retain their starch structure, and resist sprouting for many months after harvest. When truckloads of potatoes arrive at the factory, all the raw ingredients are unloaded into a recirculating whirlpool washing system. Inside, high-pressure water jets combined with continuously moving chain conveyors create a powerful swirling current that makes the potatoes gently tumble against each other, washing away mud, small stones, and other impurities clinging to their surfaces. A standard industrial wash tank in a potato processing plant like Pringles can hold up to 40,000 liters of water, allowing it to clean between 20 and 25 tons of potatoes per hour. After the first rinse, the stream of potatoes passes through several recirculating wash tanks, ensuring all soil and debris are completely removed. In the final stage, the potatoes enter a rotary drum washer, a stainless steel cylinder nearly 5 meters long. Inside, the drum rotates slowly at about 10 to 20 revolutions per minute, while hundreds of high-pressure water jets spray from every direction. As the potatoes tumble and gently rub against one another, any remaining fine dirt or residue trapped in the eyes is washed away. By the time they exit the drum, the potatoes are virtually spotless, their skins smooth and clean, ready for the next stage of processing. After washing, the potatoes move through an automated scanning and sorting system. Here, optical sensors and high-resolution cameras scan each potato, taking less than a millisecond to analyze its size, color, and surface integrity. Potatoes that are too small, cracked, bruised, or discolored are gently removed from the conveyor by air jet ejectors, separated for use as secondary material. Only those meeting precise standards of size, weight, and surface quality continue forward, ready for the peeling, cutting, and processing stages ahead. At this stage, the process enters a critical turning point. Inside the abrasive drum peeler, whose inner surface is lined with sandpaper-like material, the outer skin of each potato is completely removed after just a few gentle rotations. Within 1 hour, 10 tons of potatoes are transformed, leaving behind only the smooth golden flesh, ready to continue its journey. The potatoes are briefly blanched in hot water, causing their flesh to soften for smoother slicing. Inside a high-speed cutting chamber spinning at 1,200 revolutions per minute, razor-sharp blades slice the potatoes into thin pieces, then chop them into small uniform cubes. From there, the pieces move along a vibrating conveyor where an automated optical scanner inspects every fragment, and with just a tiny flaw or dark spot detected, a precise jet of compressed air instantly removes it from the line. From the cutting conveyor, the qualified potato blocks are immediately fed into a pressurized steam chamber, where saturated steam begins to define their future crispiness. Under high temperature, the starch inside the potatoes fully gelatinizes, allowing the core to cook evenly, while the outer layer becomes smooth and elastic, perfectly prepared for shaping. Immediately after cooking, the softened potatoes fall into a massive industrial mixer, where they are mashed into a smooth paste and thoroughly filtered to remove any fibrous residue. The fine mash is then spread over large rotating drying drums, where steam rapidly evaporates beneath the heated surface, transforming the mixture into thin, flexible sheets. As they peel off the drum, these sheets crisp and crack, breaking into dry flakes that are later milled into fine potato powder. This is the defining moment that gives Pringles its unmistakable identity. Inside a huge industrial mixer, the dehydrated potato flakes are blended with water, cornstarch, rice flour, wheat starch, degermed corn flour, maltodextrin, emulsifiers, and a precisely measured amount of salt. The result is a pale yellow, semi-moist dough, soft, elastic, and with a texture similar to wet sand, unlike the dry, crumbly mash used for regular sliced potato chips. From here, the potato dough moves onto a continuous rolling conveyor, whereas massive steel roller compresses the warm, smooth mixture into an ultra-thin sheet, just about 1 millimeter thick, soft, elastic, and perfectly uniform, like an endless carpet of starch. Under carefully controlled pressure and temperature, the starch molecules bond tightly together, forming a stable, cohesive structure, ready for shaping. The dough sheet then passes through a rotary cutter, continuously stamping out neat oval shapes, affectionately nicknamed doughvals by the factory workers. Any excess dough left between the cuts is immediately vacuumed back into the system to be recycled for the next batch. Frying is the most crucial stage for any snack brand. For Pringles, the edges of each slice are fixed while the center gently puffs up when it meets the hot oil, forming the iconic double-curved shape. This design not only prevents the chips from breaking when stacked, but also creates the signature saddle curve that no other chip in the world can replicate. And after all the transformations, this is the moment when Pringles finally receives its soul, the seasoning. Just 11 seconds after frying, each crisp is blasted with hot air to remove excess oil. On the conveyor belt, thousands of chips pass through a flavoring chamber, where a fine mist of seasoning powder coats every surface evenly and firmly. Each day, the factory uses around 2.7 tons of seasoning, producing more than 160 distinct flavors. From Japan's spicy wasabi, Mexico's fiery chili lime, to America's rich cheddar cheese, every Pringles chip becomes a tiny vessel of culture, carrying the taste of different corners of the world. And the most fun way to explore them? Stack multiple flavors together and take one big bite, because with every crisp snap, you might discover a combination you never imagined before. At the end of the production line, the perfectly curved Pringles slices stack themselves in flawless order on the conveyor belt, like a disciplined army falling into formation. The mechanical system then compresses them into a straight column, wraps them in a protective film, seals the metal bottom, and caps the plastic lid on top. Immediately after, the finished cans continue their march into cardboard boxes, typically 12 to 24 cans per case. Before leaving the production line, quality experts conduct blind taste tests under red lighting to evaluate crispiness, flavor, and seasoning balance. Only the perfect batches are sealed, packed into cartons, and loaded onto trucks, ready to join parties, picnics, and joyful moments shared by billions of snack lovers around the world. Entity. Compared to other well-known gummy brands such as Albanese in the United States, Haribo does not chase extreme softness or overly sweet flavors, instead remaining firmly committed to its traditional chewy texture, a choice that has shaped the brand's DNA for more than a century. Haribo's success has never been accidental, but rather the result of decades of meticulous refinement and unwavering consistency in product philosophy. Even the colors of its gummies are designed according to precise logic. Red appears most frequently because it is consumed the fastest, while green, yellow, and other colors exist not merely for visual appeal, but to balance flavor, consumption rhythm, and the overall user experience. Beyond that, Haribo continuously updates flavors, shapes, and production technologies to adapt to the demands of each market. So what about you? When you open a bag of Haribo, which color instinctively draws your attention first. And every journey has a beginning. Right now, let's step into the very first link in Haribo's gummy production chain, the gelatin factory, where the foundation of every gummy candy is formed. Each day, a large-scale gelatin factory receives between 50 and over 100 tons of raw materials, primarily animal skin and bones. Upon arrival, the materials are inspected for quality and separated into appropriate processing lines. Before further treatment, all raw materials are reduced in size through cutting or grinding to increase surface area for the subsequent processing stages. After being cut into smaller pieces, the raw materials are soaked and washed in large water tanks, combined with continuous agitation to remove blood, fat, and surface impurities, while also hydrating and softening the collagen structure. This is a crucial pre-treatment step that allows the chemical reactions in later stages to proceed evenly and consistently. In this stage, a large volume of wastewater is generated, containing high levels of organic matter and fats. Therefore, appropriate treatment is required to prevent water pollution and environmental impacts. Next, the materials undergo chemical treatment to break down the collagen structure, typically by soaking in an alkaline lime solution for 5 to 20 days, followed by neutralization with a dilute acid to adjust the pH to around 5-6, preparing them for gelatin extraction. At this stage, the material is heated in water at temperatures of up to around 80 degrees Celsius, allowing collagen to gently hydrolyze and dissolve, releasing gelatin into the solution. This process occurs in multiple cycles, producing a protein-rich gelatin solution that forms the foundation of gummy candy's characteristic elasticity. The raw gelatin solution remains cloudy and contains undissolved particles. To achieve the required purity, it is passed through a multi-stage filtration system with ultra-fine ceramic membranes. Under high pressure, microscopic impurities are retained, allowing only purified gelatin to pass through, resulting in a clear, uniform, and stable solution. After filtration, the gelatin is demineralized through an ion exchange system, helping to stabilize its pH, color, and gel strength. Subsequently, the gelatin solution is heated to maintain its liquid state and fed into the vacuum concentration system. The concentration process is carried out at a temperature not exceeding 70 degrees Celsius in order to minimize gelatin denaturation, while excess water is removed to increase the solid's content to approximately 30 to 40%. The resulting solution has sufficient viscosity and consistency for subsequent forming and further processing steps. After the gelatin solution is cooled to a semi-solid state, the elastic mass is pressed through perforated metal plates with precisely controlled openings, forming long, continuous gelatin strands. This extrusion is carried out under stable pressure to ensure uniform strand size and structure, which directly affects the gelatin's solubility and gel strength. As the material passes through the plates, the protein structure begins to set, transitioning from a bulk mass into flexible strands. The strands then fall onto a conveyor belt and are dried with sterile hot air, removing most of the moisture while preserving the protein structure that gives gummy candy its characteristic elasticity. After drying, the gelatin is ground into a fine, uniform powder for easy dissolution and precise dosing. From here, the gelatin is bagged and sealed by batch, ready for immediate shipment to food manufacturing facilities worldwide, as delays and exposure to moisture or temperature fluctuations can reduce solubility and elasticity, directly affecting final product quality. And now, let's move on to the most anticipated part of the journey, where gelatin is no longer just a raw protein powder, but is activated on Haribo's production lines, transforming into millions of chewy gummy candies found on shelves around the world. At Haribo factories, the candy production process begins with the careful selection and precise weighing of key ingredients, such as gelatin, sugar, glucose syrup, water, food acids, flavorings, and colorants. These ingredients are then fed into the mixing system according to pre-programmed formulations, strictly adhering to Haribo's proprietary recipes. From the very first stage, each batch is closely monitored to ensure absolute uniformity and consistent quality across millions of finished candies. After dosing is complete, the mixture is transferred to industrial cooking kettles and heated using high-pressure steam. Under controlled heat, water evaporates while sugar and gelatin fully dissolve. Within just a few minutes, the mixture becomes a smooth, uniform liquid syrup, ready for the next stage of structural stabilization. After cooling, the syrup is tested for bricks using a refractometer to ensure the sugar concentration and consistency meet the required standards before shaping. At this stage, the base syrup is divided into multiple streams for color and flavor blending according to each product. Haribo produces dozens of different flavors, with sour varieties such as cherry, raspberry, and grape, requiring precise acid control to deliver a sharp taste while maintaining gelatin stability. In parallel with flavor preparation, molds are formed directly on the mogul machine using cornstarch blended with mineral oil. The machine spreads and levels the starch, after which stamping heads press the candy shapes into the starch bed, creating hundreds of soft cavities on each tray. The cornstarch not only holds the shape of the candies, but also absorbs moisture from the hot candy mass, allowing it to set slowly and uniformly, an essential factor in developing the characteristic chewy and elastic texture. When the starch molds are ready, the gummy syrup is transferred into central depositing hoppers, where temperature and viscosity are tightly controlled to ensure precise flow. An automated depositing system then dispenses exact amounts into each mold cavity with minimal deviation. Throughout the process, sensors monitor syrup temperature and flow to prevent underfilling, overfilling, or air entrapment, allowing Haribo to maintain consistent gummy quality even at massive industrial scale. After depositing, the trays are stacked and moved into curing rooms for approximately 18 to 24 hours. During this time, the cornstarch continues to absorb excess moisture while the gelatin fully sets, forming a stable, chewy, and elastic structure. After the curing stage, the trays are inverted over vibrating screens, allowing the gummy candies to separate from the starch molds and continue along the production line. The remaining cornstarch falls into a recovery system, where it is cleaned and reused for subsequent batches, improving overall production efficiency. The gummies are then transferred into slow-rotating drums, where they gently tumble and collide with one another as the drums turn. This motion removes any remaining starch residue from the surface, while rounding the edges and evening out the shape of each candy. Once cleaned, a thin polishing layer made from vegetable oil, combined with beeswax or carnauba wax, is evenly applied inside the rotating drums. This coating prevents sticking, enhances surface smoothness, preserves color, and gives the gummies their familiar dry, pleasant feel. A small detail that plays a key role in the signature Haribo eating experience. Finished gummies are randomly sampled and inspected for shape, color consistency, flavor, and chewiness to ensure each batch meets Haribo's standards. Selected samples undergo additional testing for elasticity and heat resistance, confirming that the gummies maintain their characteristic texture and stability during storage and distribution. Only products that pass all checks proceed to packaging. Finally, gummies that meet quality standards are fed directly from the conveyor into a fully automated packaging system, where multi-head weighing hoppers continuously portion the candies according to precisely preset weights. Each hopper calculates the optimal combination in real time, then releases its measured load straight into individual bags in a split second, ensuring uniform fill levels and minimal variation even at extremely high production speeds. Once filled, the bags are immediately heat-sealed, labeled, and passed through metal detectors to eliminate any risk of contamination. They are then packed into cartons, shrink-wrapped, and stacked onto pallets, ready to enter Haribo's global logistics network. This seamless, end-to-end automated process enables millions of Haribo products to leave the factory every day, supplying retail shelves across hundreds of countries worldwide. Notably, every Haribo gummy is engineered to deliver a chew time of approximately 20 to 30 seconds, significantly longer than fast-melting candies. This extended chewing gradually releases sugar and flavor, creating a smoother sweetness, less taste fatigue, and a consistently satisfying eating experience, no matter where in the world the candy is enjoyed.